I think quantum computing is the biggest revolution in computing since computing. With quantum computers, you can solve problems that we thought were practically impossible to do with the biggest supercomputer in the world. This is a way that's going to be a big revolution for humanity. So I want to be a part of that.
Maybe it would help to talk about Twitter, which is actually how we found each other. So I think it's fun that, the coolest connections are made on Twitter. I happen to just reach out and say, hey, I need to do a quantum episode. I want to talk about quantum computing. And then out of all the recommendations, you popped up as one of the people that was the perfect people to talk to. So why don't you tell us who you are and, why you might have risen to the top of the quantum stack of people who are on Twitter thinking about it.
Yeah. So I'm César Rodríguez. I'm the CEO and founder of Computator Studios. I've been working on quantum computing for over 20 years. This is kind of my life's passion work. To be honest, the reason why I was one of the last ones on Twitter is because Twitter used to be a really thriving quantum community, and it kind of shattered the past year. That's the truth.
Oh, really? No,
yes.
What happened?
A lot changed in Twitter. I don't have to go through the drama that's happened. Everybody knows. For example, the name is not Twitter anymore, right?
That's right. It's X apparently.
So
I refuse to use that. But,
it was really a lot of communities kind of died out, and that was one of them. And I'm kind of sad about it because I missed it. It was great for gossip too, by the way.
Oh, geez. So did people go elsewhere? Did people go to is there quantum threads or something?
There's no good place. I feel very lonely. It used to be very thriving. We will have huge debates about papers. And there was drama and gossip. It was super fun. Yeah.
Why don't you set the scene for us? Just tell us what is quantum computing and how does it work and why are they so cold?
This is kind of the school of thought that I belong to. School of thought straight with history, right? So before we used to think the universe was made of particles and fields, and now we think it's made of information. And so you can go back to the Matrix movie or something. If you have enough information, you can model the universe kind of thing. Well, it's kind of wrong, the Matrix, because it was using bits. And that's not enough to model the universe. And that's fundamentally what quantum computing is that the universe is fundamentally quantum mechanical, and classical information, that's the one that you can represent with bits, it's just a tiny part of the whole information context of the universe. So what powers quantum computers is just the rest. A visual image I want everybody to keep in mind is bits, if you think of the planet Earth or something like that. So if the planet Earth, a bit will be zeros and ones, so you could think of it the South Pole and the North Pole, for example. And so if you try to describe everything in the universe just using those points, it's very limited. However, quantum computer allows you to use the whole sphere, even inside. So it's much, much more information content than that. But of course, it contains the old stuff. That's super, super important. And the idea is that with that allows you to do computational things that were essentially impossible. So with quantum computers, you can solve problems that we thought were practically impossible to do with the biggest supercomputer in the world. That's ultimately what it is. These are some very important problems. My favorite one is chemistry, because chemistry is fundamentally quantum mechanical. Atoms are quantum mechanical, of course. That's how physics started. Quantum physics started. There was a debate: what's more fundamental, chemistry or physics? And when quantum mechanics came in, physics won, which I'm very proud of that. Because then suddenly the periodic table you can derive from the quantum mechanical principles. But from that, the fundamental of quantum physics is that you can use this description of the universe, which is of course very odd. It's very counterintuitive in many ways, to do more than you could do before. So, for example, if you want to understand how a molecule works, let's say for pharma or for medicine or for new materials, you have to understand the quantum mechanics. And computational, that's really, really hard. It's super difficult. However, the way it works usually is that you take the quantum mechanical problem, you approximately heavily, literally crop it up, go with a machete to cut it off, and then you put it in the biggest supercomputers in the world, which a lot of them are used for this kind of problem, and you evolve it in time with also very approximative methods, and then you run out of money, so you stop the run. That's basically it, because there's limitations, right, from compute power and so on. And then when you're there, you kind of try to approximate back up to the quantum mechanical level. And of course, that's extremely inefficient and incomplete. This is why when you think of let's say, a chemist, you think of somebody with a lab coat mixing cocktails, right? You don't think of somebody like me that programs quantum computers. And those people are basically people with PhDs doing very, very sophisticated trial and error by mixing cocktails, right? It's extremely inefficient to do discovery that way, and it's because they couldn't do it from first principles. And quantum computers will allow us to do a lot of that, so really narrow down all the possibilities for this, because it's just better understanding the nature of reality.
And so is there a piece of the quantum computer that, like, the reason it works is because it is the same substrate or whatever as the thing that it's trying to figure out? Like, the universe is quantum. If we make computers quantum, then they can just directly simulate things in the universe. Is that basically the idea? Or is it a compute thing, though? So, like, there are two versions of it that I could see. Like, version 1 is it's the substrate. It's the same thing. That's why it works. Version 2 is quantum computers are just plain more powerful. Like, you can do 2 to the n instead of, like whatever classical computing would have in terms of bits. So if we did develop a sufficiently big classical computer, are there things that still a quantum computer could only do, like an arbitrarily large classical computer? Could it do the same sort of things as quantum, or is there something fundamental in like the quantum nature of how things are doing?
From my philosophical point of view, they're both exactly the same, because I believe the universe is made out of information, and so they're the same. It's like, what is the description of the universe you can have is what we can compute ultimately. That's really, I think, of course, this happens to be from my generation of scientists, right? Like, this might change for my son when he's a little older, right? But for now, that's not how we see. So for me, they're exactly the same. And ultimately, think about it. If you want to model the whole universe, which is a pretty darn big place, you will need a quantum computer bigger than the universe to do it. And so it has to be a quantum computer. If you want a classical computer to do it, it will have to be exponentially larger, most likely. So ultimately, it's both. It's really the nature of reality such that it's quantum mechanical, and classical mechanics is just extremely incomplete to do that. And an analogy I really like to use is the trains versus airplanes. And so classical computers are like trains. Like, they're very fast. They go on rails. They're really nice. And quantum computers are like airplanes. The physics allows them to fly, so there's more dimensions you can play with. Of course, it comes with a lot of challenges. Piloting an airplane is much more harder than being a conductor of a train. But you can go to new dimensions, and you can go to new places, and you can see things from another level. So if that's something that's something I think it's very fundamental. It's like, so what's the best description for planet Earth? I mean, trains give you a pretty nice one, but there's, of course, much higher level descriptions that we need. No matter how big the supercomputer you build, it will not be able to solve certain basic problems for quantum computer. This is absolutely a fundamental thing. It's just too hard for them.
The other piece of context that I would like to give, just in the very beginning, is like the fundamental challenges of why quantum computing is even hard in the first place. Like, I do think that people sort of know this too. Like, they've heard of maybe like coherence. Maybe they've heard of like the fact that these supercomputers have to run super cold, or like these quantum computers have to run super cold. Do you mind talking about that? There's like the very high level like challenges that quantum computing faces.
Yeah. So it's really that the same physics that make them so powerful make them very frail to errors. You can't separate those two things. It's just like airplanes. The same physics that allows them to fly makes it prone to storms and turbulence. There's just like, you just have to accept that it comes with it. And so a lot of people are like, but why do you put rails in the sky? I'm like, you're missing the point of the airplane, right? The point of the airplane goes to places you could go with rails. It's like, it's really, really crucial for the airplane. It's not just the speed of the airplane. It's like, it doesn't need the rails. That's so dramatically different. So it's the same with physics. And the main physical principle that makes it so difficult to translate these things is called the no cloning theorem. This was done by Wouters and Zurich. They are kind of mentors of mine. I really look up to them. When I was at UT Austin, I was in the office. They used to be grad students, so I remember all of that. And the no cloning theorem, it sounds really odd, but when you think of bits, zeros and one, the main thing we do is you can look at them and you can copy them. You can say, oh, I just read one, so you write it on a piece of paper, one. They call it cloning, you're just copying the information. However, with quantum computer, when you look at the qubit, you destroy the information. You do get a 1 or 0, but you don't get the full qubit superposition thing. And you can still do a lot before you get to that point, but that's really, really fundamental. You cannot copy all of it. So that makes it fundamentally very difficult to manage errors, because how do we manage errors? If you have a hard disk, you have a RAID system. What do? You just copy many times the same bits. Just keep copying them. They'll be fine, right? Like, then you have them both to do that, which is not possible in quantum computing. But that same principle that prevents us from copying the qubits is what powers the computational advantage of quantum computers. You can't have one and not the other. Like, they come together. So of course, so why are they so frail? This is, of course, like, why does the universe look classical as opposed to quantum mechanical? Why don't we see superposition with our own eyes? And ultimately, I of course I started saying this, like, the universe is quantum mechanical, but it doesn't seem like it. It does seem like the Matrix. It does seem like it's made of bits. So what's going on there? It's a big gap between them. So this distinction is called quantum decoherence. Like, how do you go from the quantum mechanical perspective onto the microscopic perspective that we use, which is the one that it kind of looks like bits for the most part, except when you happen to want to dig deep into things. And quantum decoherence happens, it's an emergent phenomena, because since quantum information cannot be copied, it's not very robust. What classical information can. So when I look at something, I get a little bit of classical information, and then in my brain it's being copied and augmented, so I can have a complicated image. I put it on the computer, fully augmented, I put it in the internet, it's like augmented, it goes into your brain, right? And so it's really that. It's really that the classical part is easy to copy, so that's why we see it all the time. It's more robust. It's a little bit like a Darwinian thing that allows it to survive all this noise. And the classical is very, very fragile. But this one, a way I like to think about it is that, why do we see the world as classical? Why is it so counterintuitive for people, quantum? And I think it really is that it's kind of our own fault. It's not that quantum is wrong. It's that our brains evolved to manage saber-toothed cats. Like, you see a saber-toothed cat, your brain knows how to run, right? Like, it's like it sends all the information, you just run. It's not designed for understanding Schrödinger's cat. and that's really why it's so difficult for us to understand, is that you need additional you need a level of abstraction that our brain is not used to, because it didn't evolve for that. But it doesn't mean that the universe is not built that way. It's our own preconceptions as humans. Yeah.
Hey everybody, quick break in the action to tell you about Coda, who is today's sponsor for this episode. Coda is the best way to keep your team all on the same page, literally. It consolidates spreadsheets and documents and anything else that you need to do planning for a remote distributed team. This is perfect for a team like First Principles, where we have people that are scattered across the country. Not everybody's based here in San Francisco that works on the show, and so we have to stay collaborative in some way, and that way is Coda. The simplest example is just choosing a set of tasks that you have to distribute across a team. We can see what progress everybody's making, whether people are on or off track, and we can just keep them all in one place. We don't have to have them scattered in a bunch of different programs. If you're a product manager, you can do your OKRs through Coda. If you're a leader at a company, you can just make sure that all of your disparate teams come together in one place. And you don't have to start from scratch. Coda has this huge document library that you can leverage to just get started and not have to start from a blank page. If you want a platform that allows your team to collaborate effectively and focus on shared goals, you can get started with Coda today for free. Head to coda.io/FP today for a free trial. That's coda.io/FP, coda.io/FP for a free trial. Let's get back to the show.
Isn't there a piece of it too that's just like the law of large numbers too? Like the fact that like the universe is quantum. Like the things in this water bottle technically are, quantum. Like all the little individual atoms are obey quantum mechanical, not classical rules. But there's so many like billions, trillions, quadrillions of atoms that are in this thing that I can pretty much know that my finger's not going to go straight through when I tap the top of it. I mean, there's like a statistical element to the scale at which humans operate that we don't even have to worry about the quantum stuff. It just like takes care of itself because it's all averaged out. Isn't that also part of it?
Yeah, so that's a big part of it. Of course, there's a way, like, when you show me the bottle, I can see the colors, and that is a quantum mechanical phenomenon. The colors are completely quantum mechanical because it has to do with the resonance of each individual atom, and the reason why I see some parts being white, some people being red, some parts being black, is really because we really see the quantumness of this bottle. But, of course, when you're going to push the finger, you're like, oh, I can't describe the Maxwell equations. It just repels each other. So there's some truth to that. In terms of the law of large numbers, I want to talk about thermodynamics because that's kind of where you're getting into. So, of course, thermodynamics says that when you have stuff that's really big enough, there's like a limit at infinity that you go to some sort of average of something. But there's a process for this. It doesn't happen immediately, although in the thermal class we like to pretend it does. It's not true. And it takes some time. And the rate of this happens is different from classical information and quantum information. So quantum information, it's usually way faster to decay than the classical information, basically. And so that's really what the universe looks so classical, is that the classical information does get averaged out, right? Like if you leave a hard disk in the sun for for hundreds of years, the information is going to be deleted. Well, the qubits do the same, just happens much faster. But it's basically the same. It's really the same. It just happens at very different rates. And this ratio of how fast the quantum information dies versus the classical information, this is really what we call decoherence. It's not just information being lost, it's the ratio of the classical versus the quantum. That's really, really what we focus on.
Interesting. What's like the fundamental reason why that has to be true? Like why can't we just build like quantum bits that are very robust? And why do we have to have our quantum computers be so cold to like not get randomly thermally messed with?
Yeah. So I'll answer it two ways. First, the historical one, and the little more modern one. So the historical one it's called the measurement problem, and so maybe some of your audience might have heard about it, which is you have a quantum mechanical thing, and then you look at it, you measure it. That's how it's called. That's how Heisenberg and Bohr and so on came up with it. You measure it, and suddenly you destroy the information. It happens instantaneously, and suddenly it looks perfectly classical. That's really, and the measurement, and at that time, it was like a really magical thing that connected the quantum world from Heisenberg and Schrödinger's equation to the classical world of particles and waves that we know. Like it was really thought as something magical, and they would say, of course, shut up, I calculate, don't ask those questions. Of course, that was over 100 years ago. So we have learned a little bit since then, and we don't think that way anymore. And the way we see it is like really the world is fully quantum mechanical. So the measurement process itself, the measurement apparatus, they'll used to tell you, yeah, well, the measurement apparatus is like you're really microscopic, and you look at one atom with your eye, so because you're big and they're small, you destroy a lot of information. We do think that in some way, but it's not instantaneous and not magical. It's a dynamical process of coupling quantum mechanically with quantum mechanical equations, and it just happens to be that as we do so, because of the no cloning theory, which is something super fundamental about the universe, that you cannot copy certain kinds of information, but others you can. So no cloning is for quantum information, but the classical ones you can. So if you want to think of the planet Earth picture, it's like you couldn't copy the whole planet Earth sphere, but if you tell me the North Pole and South Pole, I can copy those too. If you're in the North Pole and South Pole, I can tell you I can copy that right now, but I don't have the information for the other latitudes. That's kind of how it works in quantum mechanics. So ultimately what we think is like, it's like you cannot copy some kinds of information. So the ones that's very robust to these measurements, which means robust means it doesn't get erased, which means you copy it, is the classical thing. So the way to think about it is like we're very quantum mechanical. The atom is very quantum mechanical. We inspect it, but for it to get the information to get into our brain, it has to be amplified, and the only stuff that can be amplified is stuff that can be cloned. That's really fundamentally the difference.
That makes sense. I think the thing that always struck me as really weird about the whole like double slit experiment thing was the like voodoo of observation, and the atom or the particle, the photon knows that we're watching it or whatever. But what you're saying is that that's not actually like there's the photon isn't like looking back at us and knowing when it gets observed. That's not actually the thing that is causing the weird interference pattern. It's like something else. It's the more fundamental nature of like what these photons actually are.
So the more modern way we understand the measurement problem is that it's an emergent phenomena. That the classical world that we see, the bits, is really emergent. It just happens to be very, very robust emergence. And the other stuff gets kind of washed out. It just becomes fluctuations. So that's really, really, it's like we just really good at seeing that stuff, not the rest. So it's a little bit of a bias from us being humans, but it does seem like it's a pretty good bias because we are computational machines, and it does make sense we focus on the stuff we can copy because that's what they do. All the way from Turing, that's what you focus on. What are the things you can copy?
Does this mean then that that's a really good background, I think. Like that, hopefully people like at least have a base level understanding of like what is all this stuff now. I think let's hop now into more of the like what are the modern things that people are thinking about with quantum computers? How are we building them differently now? What are the real challenges that we're facing with them? And I mean, maybe a simple way to kick this off and sort of bridge from what we've been talking about, does this nature of qubits, just this reality of what a qubit is versus what a bit is, does this mean that sort of the solution can't be a hardware one? Like no matter how good we make the hardware of our quantum computers, like there's just going to be these errors because there's just this nature to qubits?
Yeah. So something I want everybody to think about is when you look at a news article about quantum computers, they always mention how many qubits the computer has. And just by itself, that number is completely meaningless. And so I want everybody, when they just see in the title just the number of qubits, I want everybody to be very skeptical of everything written below it. because it's usually, it means it's probably very superficial understanding of what's happening. And so really, of course, there's a lot of parameters that matter. I like to put them into 3 categories. I think they represent enough. Of course, it's still a simplification, but one is the number of qubits. The other one is like another axis. That one will be the connectivity between the qubits. And the third one is the quality of the qubits. So think of it like a 3-dimensional axis. Like you want all those to be very, very good. You want a lot of qubits. You want it to be very well connected in a very controlled way. So for example, I am made of qubits and you are made of qubits. You're made of about 10 to the 20 something qubits, right? That's a lot. But you are a terrible quantum computer. No offense. I'm also a
none
terrible
taken.
one. Right. And it's because your connectivity is not optimal for that, and your your gates are not the best for that, because your gates are made for something else. They're made for you keeping you alive, right? Which is a pretty good thing, right? We appreciate life. And so, but you need to do all 3 very well to have what's called a scalable quantum computer. And of course, there's like there's pros and cons of all those, and you can do some trade-offs between them. For example, if you have qubit 1 next to qubit 2 next to qubit 3, but qubit 1 and 3 are not directly next to each other, you can sacrifice the one in the middle to set information between them, for example. But that makes sense, right? A little bit of a telephone here. So in some way, you can swap number of qubits for connectivity, is what I'm saying. And also, there's ways that you can exchange number of qubits for the quality of the qubits. So this is known as quantum error correction, which is you use many qubits to support one qubit. So think of it like one of those human pyramids of cheerleaders or something, that you have many people holding one up, right? Oh, that's very high. Oh my God, it's very high. But you need all the people to be very good at holding them and keeping them stable. So that's another one. And so all the hardware modalities, what's important to understand is they are not good at all 3. Nobody's good at all 3. Nobody has achieved that. When we achieve that, that's going to be, of course, the golden moment in quantum, that we're going to, suddenly it's going to be scalable. But what everybody's good at some of those, but not the others. And they're trying to figure out a path of compromises to get to scalability. And nobody has figured it out. So there's a lot of modalities for quantum computers. I'm going to focus just like there's just too many for me to list. But just some categories of the most common ones, the ones that are easy to find online to program stuff. Some will be atoms and ions. If atoms and ions people are listening, I know you're very afraid. Don't get offended that I put you in the same category, please. I like you very much both. I don't wanna. But both of them, the strength is they can put a lot of qubits, and the connectivity is quite good. And also the error rates are really good. However, there is a limitation of how much you can scale that up, and this is really the fundamental challenge. It's like that one might work very well now, but it's unclear how it will work in the future. And the reason is they are literally putting atoms or ions. Of course, ions are just like you could take an electron out of an atom, and they're putting in a vacuum chamber. So this is like more vacuum than empty space, and they're having them surf electromagnetic fields. So literally lasers or electromagnetic pulses. It's crazy. They just have them surf each other, and they have them all like hanging out like on the waves, like a bunch of surfers on the beach, and then they make them dance together when they need to do the calculation. That's how they do it. This is amazing, right? But this is incredible that we have this level of control of individual atoms. Like this is unbelievable. Like science, there's been many Nobel prizes for this stuff. It's incredible. But this is in a vacuum chamber, and a vacuum chamber, it looks like if you think of kind of like a World War II movie, and you think of a diver, he has this big helmets with the glass panes and it's metal. They look kind of like that, and they literally in that thing. They have to put the lasers and the electromagnetic fields and the atoms and the vacuum pump, and they have to have them all dance together. And ultimately, the limit is how much can you cram into this thing? This is a special limitation of the electronics and the lasers and all that. So you can see that even if you can put a lot in one, there might it's easy to ask what's the limiting factor, because if you build this chamber bigger, then the alignment of everything is harder. The vacuum system is much harder. And this is a fundamentally hard thing. Like it's hard to picture how you can keep scaling this up and up with the current technology. So those are really good now, but the scaling is harder. On the other hand, you have these other quantum computers that are called superconducting. They use superconducting qubits, and so they use QUID devices. And some of those are like say IBM or QEM, for example. Even D-Wave tries to do some of those. and those are different in this three-axis thing. So they're probably gonna be really good at having a lot of qubits, and they're gonna scale nicely. The connectivity is kind of in the middle of the road. Like it's okay. It's not, and the reason is because they can fit more, but it's okay because they can build many, so they can swap middle qubits if they need to. Like they can sacrifice a bunch if you need to. But the quality of the gates is not so great compared to the others. But what's nice about them is that the way this is built, all the superconducting qubits, it does rely on a lot of similar technologies to silicon fabs. It's not the same, but it's all similarity. So it's easy to picture. If you can build a 1,000, you can build 1 million. Like this is not a crazy thing. And the challenge of that is that to prevent them from quantum decoherence, instead of before in atoms and ions, you just isolate them from all the observations and the rest and thermodynamics by putting them in vacuum. For those others, what you do is you still put them in vacuum, but mostly what you do is you cool them to as close to absolute zeros as you possibly can. And so that's very hard. I mean, it's hard in the sense that there's a limitation, a physical limitation of what can that be, which is a liquid helium. There's been like a lot of Nobel prizes just for super cooling. So we know the limits of what this can do. But it does seem like there's like a fundamental limitation of how much you can cool the superconducting chip with this. And if you have looked at photos of this kind of quantum computers, they often look like a chandelier. You know what I mean?
Yeah.
Like
they're crazy looking. Yeah. It's the one that Joe Biden was like, oh, whoa, when he's
yes. And he was looking at the wrong part of the computer, by the way. I love that part.
Really? Because he was looking at the top, not the bottom?
Yeah, he was looking at the top, which is where the cooling system is, and the chip was at the bottom. So it's a little bit like, oh my god, this computer is very impressive, but you're looking at the fan of the computer.
Yeah.
but in some way, it's because you can tell the chip is tiny. All this other stuff is super obvious to tell with your eyes. That the issue is you need to take all these pipes and cables that help cooling, and you have to fit them to this tiny chip, and they don't fit. Like it's like a really visually stunning image. That this is like, why are we using this steampunk machine to build a quantum computer? It's because they don't fit. Like there's no other way around it. So this is the fundamental limitation for those is really the cooling systems. And there's the physics. We know the limits. We're really good at that. But it's an engineering challenge of how do you put more stuff to cool them in? There's not enough space to do it. So, but if they figure it out, which they're getting better and better, then it's easy to foresee that you could scale this chip much, much larger. And there's other modalities too. There's quantum dots. There's photonics. There's a lot of other modalities, and they also lie differently in this qubits, connectivity, and quality scale. Nobody has figured it out. We all trying everything we can to figure it out. Some of the things I mentioned are hardware, but I do think fundamentally that a lot of it's gonna be software that's gonna support that.
Interesting. So are there differences between the atoms and ions and the superconducting versions in terms of interconnection? Are either better or worse at the interconnection step of the three-legged stool?
Yes. So the gates in atoms and ions are really, really good quality, and the information is quite robust. They're a little bit slow. That's what they always say. So they're always having a little like Fast and the Furious argument, the people from Squid and the people from atoms and ions. But ultimately, I don't think that speed is the ultimate limitation. It's the scaling. It's really that the atoms and ions, is you have to put them in a vacuum chamber. It's a little bit hard to picture how you can connect two vacuum chambers without creating a lot of noise and a lot of other problems. While the other one is just the model will be more like printing a circuit. So that does seem a little more scalable and easy to understand.
I think this is a good time to talk about gates, basically. Like, what are they? I mean, maybe it'd be helpful to ground people in like what is a gate in terms of like classical computing, and how does that sort of build classical computing, and then how do they translate into the quantum world?
Okay, yeah. So we can go a little bit back in time to ancient Greece and Aristotle, right?
Nice.
Classical computers, of course, use logic. Zeros are false, true or false, and this was encoded in Greek times, and we know this as classical logic. And if Aristotle came from the past into now, and you explain him how a microprocessor works, he will totally understand the fundamentals. Oh yes, it just does the computations for the truth table. He will get that. This will be very familiar for him. Quantum computers, because they use another kind of information that's not just true or false, right? It uses other things, and he will not understand that. This will make absolutely no sense for him, and he will be very, very upset and about this, probably draw a sword or something at you. And so of course, like, what is a gate in classical computers? Let's say you have a 1, and you get turned into a 0 and a 0 to a 1. That's the NOT gate. And you can have 2, let's say 1s and 0s, and then you come at AND gate or an OR gate or an XOR and so on. And just from those basic principles, you can build a whole microprocessor. That's ultimately how we see it. Like, any microprocessor always build off those fundamentals. And quantum computers are a little bit different. In classical computers, a lot of those gates, if you think about it, some have the same number of inputs and outputs, like the NOT, but most of them don't. Most have 2 to 1, right? Like, this is a choice that we made as humanity. Like, it's good enough. If it was good enough for Aristotle, it's good enough for us now. But that does have a thermodynamic cost, because it means fundamentally you're erasing information, and that's why computers heat up.
Interesting. Yeah.
That's because you have more bits at the beginning and at the end, always, and that's why computers heat up. Like I can hear my computer fan going off right now, and sometimes your phone gets warm in your pocket, right? And that's exactly that. It's like you're destroying information that increases the entropy of the universe. There's nothing we can do about it. And so in the 70s, Charlie Bennett started asking a lot of questions. He was a researcher at IBM, and he's now one of the founders of quantum computer. He was really obsessed with, can you build classical computers that have the same number of inputs and outputs just to save energy? And he came up with models for that. It turns out you can. We don't do it because whatever, chips are cheap, transistors are cheap. But in principle, you could totally do it. And then he started thinking like, then what's the next thing? And he said, well, quantum mechanics is fundamentally like that. Maybe we should, and that's why he got interested in quantum mechanics. He was not a quantum physicist. It was really, he just wanted to make very efficient computers in terms of energy, and he started asking questions about that. And he went into the deepness of quantum that way, and now he's of course one of the founders of the field. And the logic gates we use for quantum computers, some are similar, but some make no sense. For example, instead of NOT, you can have the square root of NOT. So if you think of like the planet Earth and like the globe, and the North Pole is 1 and the South Pole is 0. So if you do a NOT, it's like you flip it around completely so that the South Pole is pointing up now and the North Pole is pointing down. That would be a NOT. So in quantum computer, and that's all you can do, because the only thing that matters is what's up and down in classical computer. In quantum computer, you can build it just sideways, so that the North Pole and South Pole are sideways. And that would be the square root of NOT, for example. And there's a lot more things that you can do like that, which is really ultimately what this deals with is, what you're doing is you are taking this quantum mechanical information, getting it entangled, getting into very complicated quantum superpositions, such that you massage them into doing a computation for you, simulating some quantum device, and at the very end, then you measure it, and you get some probabilistic result. And then you do this many, many times, and if you did it well, you get a really good probabilistic distribution of what the correct answer is. So you do everything quantum until the very end, and that's when you measure it, and then you start getting statistics. And if you try to measure in the middle, you ruin the computation. It's like, no, you're not allowed to open the oven before the cake is done. The souffle, if you do it with a souffle, of course, the souffle collapses, right? So it's like that with quantum computers. Like, you can, if you do measurement in the middle, the souffle collapses. And that's a little bit what happens with this quantum decoherence, is that this loss of classical quantum information to the environment, to temperature, to the air, to all these things, like this fragility, it works a little bit like opening the oven of the souffle a little bit, and that destroys the souffle. Mm-hmm.
So I know that in classical computing, you can basically take just those super, super basic building blocks and then demonstrably prove that you can do anything with them. Like, if you have the certain set, it's like complete, and that complete set of very simple operators allows you to do anything. Is there an equivalent, like, completeness set of gates within quantum computing?
Yes. So it has been proven that as long as you have some basic gates that fulfill certain criteria, you can do any computation with that. There's a challenge to them, because the ones you might build might not be the most robust to the noise. So there's always like a little pushback. Yeah, in principle they will work, but maybe you want to build ones that are a bit more robust to the noise. Like you know, it's the same that in principle you can have the human pyramid with the cheerleader at the top, with any humans, but maybe you want to put the bigger, tougher humans at the bottom.
Yeah, totally. And so basically what you mean is there are multiple discrete sets of these complete instructions that have been found or something. And then the question is, and maybe there's even theoretically more out there that we don't know about yet.
So as long as he fulfills the central criteria, it's okay. And it's very easy to compare between them. It's not a big mistake. Like you can, if you know one and you want the other, you just use a very simple mathematical transformation.
What are they? Are they? Do they map roughly similarly to sort of the and or not stuff, or is it? Are they just super weird?
I love Dawn because of the it has the same number of inputs and outputs as I said before.
Okay, yeah, right.
But the not does, but the square root of not, it's a little weird, but it does also, it's a little weird, but it works. There's all this like Hadamard gate, which does have a classical analog. There's, but a lot of them we like to think about them in terms of rotations. That's why I was mentioning the planet F rotating it. But very quickly, our geometric interpretation, it just stops working because although I'm using the sphere for discussing a qubit, two qubits are not really two spheres. It's a completely different mathematical element on SU4, and it happens to be a coincidence that I can describe the qubit as a sphere. So you have to think of them as rotations on higher dimensional complex space that they have no visual interpretation. That's something normal. But all of them are really switching around, swapping things around a little bit in that high dimensional space. And this is similar to Fourier transfers, for example. Fourier transfers are a rotation from, let's say, time to frequency domain. A lot of the quantum gates, that's exactly what they do. And there's Laplace transformations are another one that's a rotation. And there's so many interval. So a lot of in quantum are very similar to those, but it happens to be in complex space always.
So when you're doing a gate that has more than one qubit entering or whatever, do those always entangle? Is that what it means to have two qubits go into a gate? Is that they entangle with each other and then some crazy stuff happens afterwards, or is that just a certain subset of them?
Yeah. So the gates, some gates entangle. And some gates do other things that are non-entangling, like rotations of the superposition, creating superpositions. However, when you put them all together and you look at the quantum algorithm, the quantum program, we describe the quantum program in terms of gates, which is something that's super confusing when you think about classical compute. Because in classical compute, we do not program by building circuits. We don't. The circuits are already printed in a fab, right? Somewhere in the other side of the world always. It's already determined, it's fixed. In quantum, we're always dynamically reprogramming the architecture. So this is very, very different. It's something I want to emphasize. But all the quantum programs, they always have this pattern. Is you put the information as bits, right? Like you want to encode a program as something you want to solve. Let's say the energy of some molecule, you put it as bits. And then you use some gates that entangle all those bits. Then you do additional computations with more complicated gates that kind of shuffle things around at the rotations. And then at the very end, you do quantum measurements to get bits out. So you have bits in, bits out. But of course, when you have the bits out, this one, you have destroyed the computation, but you got some information out. And then you repeat this over and over to build the statistics. So always you start classical information, then you entangle it. So in some way, there's a layer of gates to do that. Then you have the middle part, that is the actual computation itself. And then the end is, let's inspect the result. Let's open Schrödinger's cat's box, kind of step.
Cool. So this is a good time to transfer into talking about what these things actually do. So how are we actually using them today? What are the actual algorithms we figured out, didn't know how to run? I mean, it seems like, given how crazily unintuitive it is, it seems really hard to even discover these algorithms in the first place. I know of I think two, I definitely know the Shor's algorithm is one of them that can run on quantum. And then there's Groves or something is another one of them.
Grover is the search, yes.
Grover. Okay, nice. So I know that those two exist. Are there tons more or just a few more or okay?
So there's many. Of course, you have to think about this. This is discovering algorithms like Alan Turing was doing before he had computers to program, right? In some way. And right now we program computers, we never think, I'm going to write an algorithm. You just program the dark computer. And if it works, right? This is when we talk about algorithms, the really abstracted version that we have proven to certain limits of computability, how powerful they are. I always like to say that complexity theorists are the most unreasonable people you'll ever meet. And I like them for that. That's why I love them, because when they say something, they're really, really darn confident that it will always work. No matter if it's an absurd situation, it's going to work. So when you talk about algorithms, the ones that are proven to that extent. So I mentioned one that I think is the easiest to understand, which is quantum chemistry. Because that's an algorithm. It's like you take a quantum problem, you map the energies to exactly the gates to simulate coupling between different energy levels, and you get out that result of the quantum molecule. And this is called quantum simulation, this kind of method. And that one is, we think that since the universe is quantum mechanical, we think it should be very, very efficient. There's no proof of that, but we have good reason to believe that this is an exponentially hard problem. Classically, maybe this is going to be linear. Maybe it's going to be very efficient. Like there's like good reasons to think about it, but this haven't been shown by complexity theorists. On the other hand, you have the two algorithms you mentioned, which is what is Grover search. So search algorithm is the one where you have an unstructured database. So this is like you have the phone book, but instead of looking by last names and finding a number, you're looking by numbers trying to find the last name. So you're doing it wrong. So if you want to be very sure, you have to look at every page, every number in the phone book, right? Like all the ends. So if you have n numbers, you have to look at all of them to be sure. And with Grovers, you can do square root of n, which is crazy. Because that means you don't have to look at 100, you just have to look at 10, right? And really the way you do it is that you take all the phone numbers and you entangle them, and then you do some quantum messaging that increases the probability of the correct one so you can read it more often. So that's Grover search. That's a really important one. And a lot of quantum algorithms, all quantum computing has that one as the baseline. We have very good reason to think quantum computers will always give you a quadratic performance improvement over any classical thing. And it has to do with the nature of the physics of how the wave function works. It's always squared. There's always tricks you can do. But we want to do a lot more than quadratic. Quadratic is awesome, but we want to do more. And that was when Shor's algorithm came about. Peter Shor, of course, a famous mathematician from MIT. I thought many years with him. He's a fantastic guy. He's always mentioned as he really destroyed the complexity theory classes, which I love. I love when people upset complexity theorists. And he really tried it because we really thought that factoring was a very difficult computational problem. And factoring numbers, so you have a big number, one of the factors that you multiply and comprise it. And of course, that's the basis for RSA encryption, which is kind of the workhorse of all kinds of privacy we use now, like the internet and so on. It's really the workhorse. Like you couldn't have working credit cards, and if you can break RSA, you can steal all the money in the world, right? Like this is like James Bond villain kind of level, right? Like this is Fast and Furious 10 kind of like threat, human threat. And
they're at Fast and Furious 100 now. 10 is old news.
Yes, that's right. So 11, we have to go up to 11. That's right. I haven't seen 10. That's why.
Yeah.
So the reason is because we thought all encryption, as we know it now, classical encryption, I like to call it, is based on you make assumptions that your enemy will not have a computer too powerful. That's your assumption. We assume you think of your enemy, the person you don't want them to look at your text messages, they couldn't have a computer so powerful it could crack this code. And that was a good assumption for a long time. But what Peter Shor did was he shattered that, because he showed with a quantum computer you could very efficiently crack that. So suddenly, what was unimaginable for your worst enemy now is totally doable. So of course, that has a lot of implications for defense, and there's a lot of geopolitics around it. The story tells itself, right? And so a lot of people say like, yeah, but it doesn't matter. You can always come up with a new algorithm, and you can have a bigger encryption key. But that's kind of missing the point, because the data you had created 10 years ago, they can crack it. They have, because they copied it and they can crack it. So if you had nuclear codes, like they have them now. And but also it's that the point of Peter Shor's algorithm is not that he happened to crack one encryption scheme. It's that assuming your enemy doesn't have access to powerful computers is not a very safe thing. That's really, really, really the message. Like, you shouldn't assume that. That's just stupid. Like, that's just wishful thinking. Like, don't put your deepest national secrets assumptions of that. Like, it makes no sense. It's just too weak. And of course, for that, there is what we call quantum encryption, which is another method that uses the same physics I was telling you about. That if you measure quantum information, you destroy it. So you encode it in a certain way that if there's an attack, when they attack it, they just ruin the information. It's gone. They can't ever read it again. And so that one, what's nice about that one is that, of course, what challenge is that you need qubits, you need a new internet to transfer those qubits. But what's nice is that the assumption there is that your enemy cannot break the laws of reality as we know them. That's much higher than assuming that I have a very powerful computer, right? So fundamentally, we think like that was very transformative in Schroeder algorithm because it completely changed your perspective about what encryption should be, what security should be. That's super, super dramatic. So those are the big ones. However, there have been a lot of other applications of some of these algorithms and variations of this algorithm, some changes on that. And they have a lot of applications for logistics, for pharmaceutical, for chemistry I mentioned, for materials, for finance. And a lot of them are a little bit based on the Grover quadratic improvement, because for them, quadratic improvement is actually a lot. Like, that's really significant for some solutions. So we do think that for some of these large optimization problems, as broadly defined as possible, that the quadratic performance of quadratic quantum computers might be very, very useful. With that said, I expect us to discover way more algorithms in the future. A lot of developments in algorithm computers was really come from programmers, just trial and error and figuring out how things work in practice. And so we're at the beginning of that stage, because we are now working quantum computers. We're still trying to figure out how to use them in practice, as opposed to just on a piece of paper to like come up with the algorithm. No programmer starts this like writing in their head the whole algorithm how it's going to work. They just do little pieces and just stitch them together. And I do think we're going to make a lot of progress that way.
How many quantum computers are there in the world?
I don't know, but I would say probably several dozens, maybe close to 100. Yeah.
Like less than 1,000, definitely though. Like there's still not like
less than 1,000. Yes. So some are getting. So it's a bit hard to say because there are some that are like a little old, so they take them offline, but they still exist. So maybe if you know the right person and they open the closet door, they can give you access. But there's not. It's a little bit like that.
That is so interesting. I mean, just imagine a world where there are only 100 computers. Like that's the stage we're at. That's literally the stage we're at. It's like, oh, why is there not more applications of these things? And like, why is there not more algorithms or whatever, more use cases that are really in the world? It's like, well, dude, there's like 100 computers right now. Like we're figuring things out still.
And if you talk to anybody that program quantum computers, the first thing they're gonna always complain is how the queues. You're always waiting in the queue. You never know when your program is gonna run. It's very efficiently done. The hardware providers, they don't care at this point to optimize security. Whatever. We don't care.
I remember reading back in like 2020 or 2019 or something that Google had like achieved quantum supremacy, and that meant that, like, in my mind, what that meant was, oh, now we have big enough qubit systems that are so big that they can do calculations that no classical computer could ever do. And in my mind, what that meant was, okay, now we're quantum supreme or whatever. We're all just going to have quantum computers now. Like, why would we ever have classical computers? Because we have achieved supremacy. But of course, that hasn't happened yet.
Right.
Even though we have these massive qubit systems. So it's like, what even is quantum supremacy, and why did people think that it was the end all be all?
Yeah. So I want everybody to think of like quantum supremacy. It's a very technical term, and what it means is there is one problem. It doesn't matter which one, that the quantum computers outperform any known classical computer. That's what it means. It doesn't matter which problem it is. So it could be touching your nose by pulling your arm around your head, something like ridiculous like that. Like, it doesn't matter. So the first step to show that quantum computers are more powerful is to build quantum computers that are really good at one toy problem that you made up, hoping that the classical computers are bad at it. So in some way, it's like you're defining the problem to make it look good, right? You're defining the criteria to make it look good. And I'm not mocking this. Like, I'm very good friends with the people in Google that achieved that and so on. This is important. This is an important first step. You have to start there, right? It's like you just want to come up with a criteria, you look better. And so that one, that announcement from Google was like that. But unfortunately, what happened was that once they announced the problem they were at, somebody came up with a really clever classical algorithm that could do it.
Oh, interesting.
So and there have been other announcements like this from Chinese groups, from IBM, and this is always happening. This is back and forth. Unfortunately, from the news, they make it seem like it's every step is dramatic and a revolution, as opposed to continuous grind, which is what it is.
Totally.
And so they're like, oh no, they must think everything is wrong. Everything on the table is no. That's how it's supposed to be. You're kind of pushing it, and then classical computers push back. That's how it's supposed to be. We should expect, though, that soon, let's say like a year or two, that then there's like a clear winner. Like that would be a reasonable assumption. We don't have it, but we should be like, or closer and closer to clear winner. It will take longer and longer to figure out how to push back. And however, remember, this is still a very artificial problem that was created to make the quantum computer look good, right? It's not. This is not a practical application. Then what you want to do is to get to practical applications, and some of those artificial problems, they do have the beginnings of scratching the surface of a practical problem. Some of them do, some of them don't. So later, what you really want to achieve is, can you do something a little bit useful for somebody, even if it's a very narrowly targeted kind of use case in chemistry, let's say, like that will be the next level. And then of course the final level is it's when your cell phone calls a quantum computer, right? That's really, it's like, yeah, it's like a very complicated logistics thing, and it just like, you don't even know it. You type it in your cell phone, it calls a quantum computer, you get the result out, right? And that's really when it becomes useful for everybody. But there's a lot of things to achieve. At the very end, the quantum computer has to be very very cheap, right? For you to justify using it, and very robust. The previous step before, when it starts to be a little bit useful, you can picture some big international companies, let's say pharma or logistics, that have a lot of money to invest in these problems, that they find usefulness for that. But we are not at the stage where quantum computers, we use them because they're useful, or they're not cheaper. They don't make our life cheaper or faster in any way. They don't help us in any way. We're not there yet. Mm-hmm.
Yeah, not there yet. I mean, one thing that I realized recently, or that I learned recently, is that there's a difference between qubits and logical qubits. Can you talk about that? So when there's this what was the most recent one? Like over 1,000 qubits, like the IBM one, the one that was just released. But that system might not have that many, like, quote unquote logical qubits, even though it has that many physical qubits. Can you talk about the difference between those really quick?
Yes. So remember when I was discussing that you sometimes use many you have a human pyramid, and you have a lot of people supporting one cheerleader at the top, right? So it's that difference. It's like, oh, we have a cheerleader that's just really high. That's a logical qubit. But there's like all this supporting.
Based on that, and based on what we were talking about earlier, which is that there's this no copying principle that's like super fundamental. Like, how do we get those gains by things other than copying? Like, it sort of seems to me that those logically are fighting each other in my brain. One is saying, oh, there is actually a way that you can have a qubit that is supported by other qubits. And then the other one says, well, you can never copy information. So in theory, each qubit is totally independent from each other. Like, how do those two things interact?
Yeah. So it's really about the structure of how you connect those qubits together, such that together they're more robust than the sum of the parts. So if you think about the human pyramid, like sometimes, like, so you hold the shoulders of the other person, they hold it to you, and you're really robust two people. Well, if you hold a single leg, it's much harder. You have to be way stronger. So it's really that kind of structure that you distribute the load in such a way that together you're more robust. There's some assumptions to get there, though. You have to be strong enough, or in a qubit, you have to be robust enough or quality enough that you can help that. Because if you're too weak, then the people above you are going to fall on you, and you cannot keep going, right? So there's some assumptions that the qubits have to be good enough and the gains have to be good enough that you can achieve this scalability, which is called quantum error correction. Which is, by the way, this is the one that gets more press. But it's just one of many things you have to do to manage the errors. This is just the lowest level. There's all the layers on top.
I would love to spend. So I definitely want to get to that, because I know that's what your company is doing. So we'll get there. I think I'm curious to hear a little bit more about quantum error correction, though, and like physically what's happening, or like how the supports, like what does the support actually look like for like the pyramid? Like what are the ways that quantum error correction actually corrects or actually helps out other qubits, like has qubits help other qubits?
Yeah. So for quantum error correction, you need all those three axes that I mentioned. You need enough qubits. They have to be connected just the right way, well enough, and densely enough, and then you have like a certain threshold of quality for the gates. And if you do that, you can come up with structures of how they support each other that together they represent one big qubit that is really, really robust. And the idea is, like, if you have all those three thresholds high enough, once you do that, you can do two, you can do many, and you can keep scaling this up. So it's really transistor moment at that level. That transistor, of course, it's above that, just like exponentially like increases, amplifies stuff. So that will be that level that we will reach, that you find the right framework such that You can keep building them and keep adding, and they won't fall apart on you.
But like, what are those? But like, what is this? What are those structures, or what is the support that they're giving each other? Like, I still don't really have an intuition for what that actually is.
It's really the quantum gates that we were discussing before.
Okay.
It really looks like that. So it's really like you connect the qubits in a specific way with specific quantum gates, and use specific measurements at certain times and so on to really add them all many like one qubit. So it's really like you input many qubits, and the output is like one qubit that happens to be better than all of them. So it's really a quantum circuit. It's quantum circuits all the way down, basically.
Okay, got it. Okay, that makes more sense. So there are certain basically circuits of qubits that together can approximate a qubit, but the circuit is more does it have longer coherence times or something, or it just has that's basically is that the main benefit?
That's the main benefit. That's the main benefit.
Okay.
It's basically it spreads out the coherence among many qubits in such a way that it affects less, basically. Which is really like the human pyramid, that you kind of distribute the load just the right way so nobody gets too tired.
Okay, so let's talk about the other ways that people correct for errors in quantum. So there's quantum error correction, which is like the kind of most popular way or whatever, the one that most people are thinking about.
That's the holy grail. That's the holy grail. Because it needs a lot of improvement in hardware, for example, and we don't have a good path. We're hopeful that this engineering problem can solve, but it's hard. It's still very hard to make improvements. There are being improvements. It's continuous improvement, but this is why when people are pessimistic about quantum, it's because we haven't achieved that yet at the hardware level, and that's I'm not pessimistic, but that's absolutely the truth. We haven't achieved that. We can't have that scalability yet. But there's other things we are doing now on top of that to improve it. So another one is what's called error mitigation. There's a lot of companies working on that. And error mitigation is really like control techniques like from electronics or mechanics, just applied to quantum problems. So it's really like when you put a broomstick on your hand and you're trying to balance it like upside down, it's really like you move it dynamically. It's really the equivalent for that for qubits, to prevent the errors from falling apart. Like you have a qubit, you don't want it to fall off, you balance it like a broomstick in your hand. So that's the kind of thing like people do with error mitigation. This is done not necessarily with gates, although some things can be done with gates. It's mostly done at a lower level that's called the pulse level. So that means that for error mitigation, you need access to the hardware at a very low level, essentially. Basically, you have to beg for permission for them to let you put a box next to their quantum computer.
Pulse level, what does that mean? What is a pulse?
A pulse level, it's that the gates, remember the gates we were discussing was like logic, right? Like ANDs and ORs and such. But ANDs and ORs are, of course, made of transistors or vacuum tubes back in the day with electricity and so on. And they had limitations how many you can plug in together. And you have voltages running for them, and the shape of the pulse matters. And this ringing is really the level of the ringing of the pulse. So it's really low level. It's like you're trying to
change the frequency with which electricity is flowing through these things.
Mm-hmm. Yes. So really, what you really do is, instead of a gate, you really want to control. It depends, of course, on the application, but you really want to control it at the sub-gate level, like lower than the level, to do this balancing act of keeping them stable.
Yeah, that seems like obviously hard to do if you're not one of the 100 people that has one of these computers.
The techniques are very mature, but there are limitations to them because sometimes when you're doing something, it affects all the qubits. For example, like these assumptions we make to simplify things, that the qubits are not correlated, and that's not true. They are correlated. The noise from one qubit does passes to the other. What I do to one qubit does affect a little bit the one away from it. Of course, it's first order. It doesn't matter. But when you're doing big computations, it matters a lot. So you do have this crosstalk between them, and that does affect each other.
Interesting. And so your thing is different than both of those. You're not working on error correction or error mitigation. You're working on like a secret third thing. Do you want to tell us about what it is?
It's also secret. It's another problem that we call algorithmic qubits. And these are the qubits that these are the errors that you can only, so it's algorithmic errors. These are errors that you can only see when you actually run the whole circuit. And the premise is the following, is that for all the things I told you before with error mitigation and error correction, there's assumptions that we make so we can do the math. For example, we assume the qubit errors are of a certain kind that are very, very simple in some way. They're Markovian, for example. That's one of them. We assume they're not correlated to each other. That what I do to a qubit does not affect the other one too much that it matters, and so on. And this is true to some extent, but when you do the calculations, you realize it's not quite true. Like, what you do now does affect the future circuit you run a little bit. And these are called algorithmic qubits. You cannot manage them on just doing these very fast-paced short-term things. You need like much longer-term applications. So the way I like to think about it, it's like the waves on a surfer, right? That it's not just the average, right? Like people assume like the average is for quantum error correction, so it's like the tide. Oh, the tide is high, the tide is low. Yeah, that's pretty good, but you don't surf the tide, you surf the waves. And you have to feel the wave, and you have to get the right timing for the wave, and other surfers affect your ride. Like you've seen, there's fights between surfers all the time because they do affect each other's ride, right? If you're tired from before, it affects your ride. All these things do affect how well you are, and you have to feel it has to be a very dynamical back and forth. And I think that the way we do quantum computing now, in some way, all quantum developers that know enough physics, they do sense this. Like they do it a bespoke way. For example, and when you submit a circuit to quantum hardware, and the quantum hardware is calibrated and they tell you what are the error rate parameters. These are very approximated. The errors are not. They don't study the errors as complex as they really are. They give you a rough estimate of the errors. And so then they calibrate the computer, and they let you start submitting jobs. So there's a whole lore. It's a little bit like wishful thinking or like boxers that don't like to fight on their blue moon or stuff like that, crazy stuff like that. So there's some physicists that say like, oh, I better submit early in the calibration window because the qubits are the best. They're fresh out of the oven kind of thing, right?
Yeah.
But then there's some people saying like, no, maybe I want to wait for the middle because then they have stabilized, and when I get statistics, they're more consistent with each other. And this is really algorithmic errors like screaming, look at me, why are you ignoring me? Of course, what you really want to do is, no matter when you submit the job, if you want to do enough you want to understand the errors well enough, then you can do data analysis at the end to put it together. So you have to analyze the errors at the beginning, do the run, and then do specific mathematics to aggregate all the errors in the clever way that you don't wash out stuff. And that's really what we do. That's really what we're focusing on. It's like we have made some scientific discoveries for specifically understanding the most complicated kind of errors, and we can add them to existing code off the shelf to help it improve its performance on the quantum computer.
How much of this is like algorithmic or like mathematical laws that you have sort of discovered versus just like raw statistics of like we've seen a million of these trials and we know that they tend to be like this? Like, do you understand those errors down to the like fundamental physics reasons they're happening, or is it just like we just know that they're there, so here's how we can correct for them?
Yeah, so there's a whole continuum between those two extremes. So if you try to understand it fully mathematically, then the cost of understanding is so high that you don't get much performance from the help it gives you. And of course, on the other end, if you're too naive, then you don't get good performance at all, right? So what we're trying to do is really get the sweet spot of this. And for this, we do use basic statistics techniques, such that from a little bit of data, we can predict what's going to be the next thing, and we can suggest ways to improve the next few runs of the circuit to then kind of loop up, right? And then the end user gets the results out. Let's say a finance guy looks what a good finance portfolio looks like. I don't. Or a pharma guy that knows how a good protein looks like. And then what they do is they run something and it's never good enough, and they want to try a slightly different parameters. So we allow them to improve those knobs to then have it run again with that. And of course, as we're doing that, what we're really doing is really gathering a lot of data about how the quantum computer really works. And that allows us to take some shortcuts such that we spend less and less on characterization. So ultimately, the more usage we get on the same hardware or with the same program, either it can be both are better, but it can be either one, then the more performance we can provide. And we really think that this is always going to be an element that's very different of quantum development that does not exist in classical developers. Classical developers, like, you just write a code and like it's done. Like you just like compile it and it's done. It's like there's not this dynamical element because it's really like a train. Ultimately, it's on rails, and the piloting is very, very dynamic. You always have to work around the storm. So our thesis is really that quantum development fundamentally is different. We have to think about it different. The workflows have to be different, and this is one of the new tools that people will be using.
Fascinating. So is this a tool that runs only after each run, basically. So like you do a one pass through, all the algorithms run, you get your answer. Then you're like, the answer wasn't quite right. Let's do something different than the next time. Like that's the place where it inserts. It's not like a process that happens during the calculation. It's something that happens to help you set better parameters, basically in between runs. Is that true?
Yeah. So when you submit a quantum circuit, remember you have to run it many times to do statistics on it, right? So it does it in between those, and it does recompile the circuit live, essentially, using some specific techniques for that, such that it's like, oh, I learned a little about this error. Let's just switch around some qubits because it's a better way to work around this error. And so you do get some statistics. Then after you have compiled enough, then you can come up with other clever solutions you can do, and you can keep improving and improving. With that said, there are some patterns to most quantum algorithms that we can reuse over and over. I told you there's always the layer of entangling things, the layer of measuring things, they always look the same. So there's some solutions that just, like, once you know for one,
just
you
work.
They're very cheap to reproduce for others. Some of the parts, not all, but some of the parts are.
And how different are different quantum computers from each other for this? Is it something that is, because you just mentioned some of it is like algorithmic or whatever, does that copy paste across from like IBM to whoever else's quantum computer, or are there like hardware specifics that you're also like learning about with this?
Yes, so there's different modalities of quantum computers. We're focusing on all the ones that are gate model based at the gate model. There's some others, for example, we didn't go into them, but there's annealers, for example, there's photonics. They use slightly different way to specify the problems. And the reason why we're focusing only on gate model, which are the atoms and the superconductors that I mentioned, is not because the technique doesn't work for the other, but because there is a standard that we developed as a community for what is the proper format to write quantum circuits for them, and we call it CHASM. CHASM with a
CHASM.
So that's the standard that we use, and that means that as long as they support the standard, then the techniques work for all of them. So that's an advantage that this algorithmic approach has, as opposed to error mitigation, where you actually need to beg the hardware provider to let you into the room with your box and connect it, right? This is very, very different. And I don't see them as competitors. I see them as complementary, ultimately. Like you do want all of them. Just like to have a good airplane that flies very well, you do want to have very good aerodynamics that works really well in the wind tunnel, but you also want the pilot to have a radar and good weather models too, right? You want both, right? So we see ourselves as kind of the radar, the weather model, such that the pilot can plot the best and more efficient route through the store.
Is there an interaction, I guess, between you and the quantum error correction folks? Like, are there things that you're learning that can help inform better error correction and like both of you working together? Or is it a trade-off? Like, okay, once we have quantum error correction, this algorithmic stuff is like less useful, or vice versa. Once we have the algorithmic stuff, we don't even really need quantum error correction anymore. Do you see it more of as like a competitor thing, or as more of like a we can work together sort of thing?
No, it's really complementary. Like, you want all those layers to be done very, very well for the optimal flight. You want them all. And I do think that as error correction matures, for example, the computational power, that there will still be these algorithmic errors. They're still gonna be there. There's gonna be less of them, but then the computers are gonna be so big that it's gonna be very difficult for developers to track them by hand. So you still want automated tools to do that for you. So we do think that that's always going to be a crucial part that's fundamentally different from how we program classical computers. There's no analog to this issue in classical computers. And so ultimately, you want all the pieces for the computer to work very, very well in the architecture.
So we mentioned really quickly at the beginning the difference between, like before we even started recording, about probabilistic computers versus like quantum versus classical. I would love for your take on just like what those are and why they work and what they're good for and how they relate to quantum.
Yeah. So I was telling you. So classical computers are like, if you take the globe or the Earth, it's North Pole and South Pole. Probabilistic computing is if you could use the information on the whole axis between the North and the South Pole. So that whole line. So it gives you more. It does give you more. But it's not quantum. It's fundamentally, it gives you like there's like this. This is what I trust my complexity theory strength. And you don't get a significant advantage on our. In practice, that doesn't mean much. Like, it could be that you get in practice a good advantage, like ultimately. But in principle, from the complexity theory point of view, it's kind of the same category. It's a little bit like, oh, it's like trains versus motorcycles. Like, yeah, like it's like, yeah, I mean, both are kind of neat and they're different. Like, you do want, like, you can go in the motorcycle places you cannot go with the train. the motorcycle is not an airplane, right? It's like really, really different. So I see them like that. It's nice. I think that ultimately we need many kinds of computing for so many different problems, and there's different criteria we should use, which is computational power is one of them. But for some problems, you don't need all the computational power, but there might be energy advantage for some of them. And so I do think that we're gonna be computation in the future, because it's gonna be so important for humanity, that we're gonna really think on more dimensions of what does it mean for us. Just like when I live in Europe, so when I'm gonna go somewhere, I sometimes take the bus and then take the train and then take the airplane, right? Like that's how in life works.
Yeah, totally. I mean, I guess to sort of like take a step back and like think about this higher level. I mean, you could be spending your time on anything. Like you could be working on the pharma itself, or you could be working on classical computing, or you could be working on this probabilistic stuff. Like what keeps you so excited about quantum, and why have you dedicated your career to it?
I think quantum computing is the biggest revolution in computing since computing. It's really that much. It's like I got interested in it when I was a teenager in Puerto Rico. I just loved asking questions about the limit of computability and what does it mean for the mind, what does it mean for reality and such. And very quickly I was just like obsessed with like, oh, quantum computing, that sounds like the thing to do. I've always been very interested in history of computing. And I'm like, oh my God, that's going to be a big thing. So I used to be a computer engineer back there. And I decided, like, after I finished my degree, I'm going to study physics. I want to do grad school in physics because I want to be part of this field. And everybody, all my professors in Puerto Rico were telling me, you're crazy. This is insane. Those computers don't exist. I'm like, I know. That's why I want to work on them, because they don't exist. I want to make it happen. And so my background really has been focusing on understanding those errors, like really the hardest problems for that. And I do think like there are some problems for humanity, like chemistry and finding new materials that are going to be transformative for us or for the future. And this is a way that's going to be a big revolution for humanity. So I want to be a part of that.
Totally. And how soon's it coming? I mean, I feel like quantum computing is one of those things that's absolutely gone through the waves. You know, it's been the coolest thing in the whole world. And then people are even talking about like quantum winter or something, like, oh, it's out of fashion now. So, I mean, for a true believer that believed in it even before it was cool, I'm sure it's easier to weather those storms. But you're still pretty positive that it's coming soon.
So of course there's the hype curves, right? And I hate those because if you look at the hype curve, right, like it's a huge curve. It goes up and then down, and there's like the valley, and then it's like continuously going up. But if you erase the hype, you will see that there was always a continuously going up, hitting underneath. It's just the hype is bad. It doesn't mean the progress is going to happen. The hype is bad. So when this happens, like I just ignore it. Like I know what we're doing. These are the roadmaps. This is what I have to do. It doesn't matter. And so in some way, like of course, like this has implications for people. Like it's easy to follow the buzzword, right? It's very easy. But I think like no, this is like you have to be before the buzzword is happening. So I am very committed to this field. I really love what I'm doing, and I do think that this is absolutely the future. So what I would tell people is like, don't get your news just from press articles on the newspapers, because they're so bad. They're really bad. Even when there's positive news, they make me cringe about how they write about them. Like I'm celebrating the achievements of my friends, but when I see a newspaper, I'm so ashamed about how this is portrayed, because it gives the wrong impression about how this is a cumulative, continuous development that has to happen. It makes it seem like one guy come up with something and it's done. And that's how the world works.
Mm-hmm. Thank you so much for doing this. This was awesome. I really appreciated you taking the time to chat with us. Any final words for people, or places you would send them, or like places you want them to check out?
Yeah. So that this was a lot of fun, Christian. So so of course, like you can reach out to me at Commutator, of course, and you can ask me more about what we're doing to shape quantum reality. I would love to chat to everybody that's interested in this topic.
Perfect. Thanks for coming on.
Okay, bye.